We're super excited to have Kaylee Hughes with us. Kaylee did her PhD at the University of Chicago, working on experiments in the Antarctic, and then was a President's postdoc fellow at Penn State before she came to Ohio State as an assistant professor. She has lots of field experience with doing neutrino astrophysics in extreme environments, so you've been to Greenland, Antarctica, and the high mountains of California doing experimental work. So ask her lots of questions about what it's like to go to really wild places. So we're really excited to have Kaylee with us today. Let's give her a warm welcome.
Thank you, everyone. It is a pleasure to be here talking about some of my favorite topics, which include neutrino astronomy, neutrino astrophysics, and some of the experimental efforts that we're doing to sort of find some of the most extremely energetic particles in the universe. So let's go ahead and get started. First, I'll give an outline of what I'll talk about. So first, I'll talk pretty broadly about what is multi-messenger astrophysics. Then we'll talk about specifically neutrino astrophysics and what we've done so far in that field. We'll talk a lot about my specific experiment, or one of my experiments, called the Payload for Ultra-High Energy Observations, also called PUEO. And then finally, if there's time, we'll talk a little bit about the future of the field. So, when you look into the night sky, what do you see? This has been a question that people have been asking for millennia, and for a long time, this is a picture that would be sort of representative of what you might see. So this is taken by a much more powerful camera, the Gaia Space Observatory. But if you look into the night sky and use just your eyes, you would see something that looks kind of like this, where you can see the plane of the Milky Way, you can see some satellite galaxies, you can see some interstellar dust. And from this picture alone, you can start to guess or infer what the physics must be in the galaxy. You can say certain, there's mass in certain places, there is not mass in other places, and you can start to understand, what you're looking at. But this is not 100% of the information that we have about the galaxy. And in recent decades, we've gotten better at using new tools to look at the same galaxy. So this is the same image, but with the Fermi telescope looking at gamma rays. And originally, you can also see, number one, there's still the plane of the Milky Way here. There's also a bunch of new bright spots that have shown up outside of the plane of the Milky Way. And you can start asking other new interesting questions about why certain places are bright in both pictures, why certain places are only bright in one. And from these two pieces of information, you can start piecing together a more complete story of what must be happening in our universe. So this is great, and these two pieces of information are useful, and we've actually gotten really good at playing this same trick. So now, we can look at the center of the galaxy not only in optical and not only in gamma ray, but in many wavelengths of light. So these are just different types of photons with different energies, and we can look at that same center of our galaxy in different light. And from this, you can piece together an even more complete picture of what must be happening in each of these different types of emissions, and from this, you can put together an even more complete picture. So this is great, but there's also one final trick that we could play, and that is not limiting ourselves to only photons of different energies, but to think about other particles as well. So this is an image I've borrowed from IceCube and NASA that shows a potential source in the universe. And whatever is creating our photons that we've already measured, you could imagine that those sources are also creating other types of particles as well. So you could have protons, you could have pions, electrons, muons, neutrinos, which will be the star of the show today. But altogether, these particles are being emitted from these sources and can be used together to better understand the physics of these extraterrestrial sources. Because as humans, we're limited to only using the messengers from these sources and not really able to go to those sources ourselves. So we'd like to talk about four main types of particles today, or messengers really, of these environments, these extreme environments. So number one, we have cosmic rays. Cosmic rays are charged particles from outer space. Often they're protons. The majority of the cosmic rays that we measure are protons, but they can be any charged particle. We have gravitational waves, which we don't have too much time to talk about today, but are really helpful messengers of some of the most energetic explosions in our universe. We have photons, which we've also talked about, and then we have our friends, the neutrinos. So altogether, these four messengers are going to be working together to tell us information about what is happening in the universe in places that we as humans can never travel ourselves. So even though cosmic rays will not be the star of the show today, I think they are quite important. And they're a really nice case study to show how far we can go with particle detectors in a span of decades. So in the year 1911, Victor Hess took an instrument called an electroscope up in a balloon and measured the radiation as a function of altitude. And he did this because at the time, there was a mystery in physics, which is that they had just discovered radiation and they were noticing that their instruments that were sensitive to this type of radiation, their instruments were going off when it wasn't near a radioactive source. And they didn't really understand why at the time. There was some question about whether it might be the ground that was radioactive or outer space could have been radioactive, and they were trying to figure it out. And what they figured out with Victor Hess was that as he got higher in the altitude balloon, the radiation increased rather than decreased. And from that, he was able to determine that the radiation was an extraterrestrial type of radiation that was increasing the closer he got to space. And this is what we now know as cosmic rays. So Victor Hess did win the Nobel Prize eventually for this work. And from that, and if you sort of go forward many decades, now we're in a position to even better measure the cosmic ray spectrum, especially at the highest energies, but across the entire energy range, we can use experiments like Auger and like Hawk to better understand and characterize those cosmic rays themselves. And that's really powerful that we're able to build gigantic detectors that are able to help us understand this particle flux from potential sources. So I'm going to show this plot a couple times today. This is a plot of flux on the y-axis versus energy on the x-axis. So this is kind of a funny unit on the y-axis, but what I want you to know is that sort of this is like number of particles. So higher is more particles, lower is less particles. And here I've included the cosmic ray flux as measured by Auger. So number one, these are extremely energetic particles. Each of these are, a single particle carrying up to 10 to the 20 eV each, which is incredible. The gamma rays that I showed you earlier are sort of on this side of the plot. And I want to talk about these cosmic rays in particular, these highest energy cosmic rays that Auger has measured. Because even though Auger has measured these, and so has another experiment called the telescope array, even though these have been measured, there's not a lot of information out there about what in the universe is accelerating them. This is a huge mystery in the field, and we want to understand what is creating them. And the reason we don't know is twofold, I would say. So number one, we have magnetic fields. You may remember from your introductory particle physics or even introductory electromagnetism that a charged particle will bend in a magnetic field, and cosmic rays are charged particles. And so that means that those cosmic rays can and will bend if they come into contact with a magnetic field. And so if you know the magnetic field really well, then that's not going to be too much of an issue. But if you don't know the magnetic field super well, that's something that you'll have to account for in your pointing. And so this makes it difficult for some of these cosmic rays to point back to their sources. Number two is that there are interactions that happen during propagation. And I have another plot that I would like to use to illustrate this. So here is a plot with nothing on it so far of distance on the y-axis versus energy again on the x-axis. And this y-axis here is in megaparsecs, which is maybe an unfamiliar unit to you. And so to give you a sense of what the scale is, our galactic center is all the way down here on this plot, and it goes all the way up here to the cosmological star formation max, which is a fancy way of saying approximately the farthest star we've seen. And so this spans sort of the distances that we might expect in our universe. And you could ask the question, if you were a cosmic ray, where can you come from in the universe on this plot? And the answer is everywhere except for this region in this top right corner. And this is because the cosmic rays will interact as they propagate through the universe at these higher energies. They'll interact with the cosmic microwave background, and you'll be limited to only using these cosmic rays for these closer distances to us. You can ask the same question about photons, and the answer for photons is everywhere except for this region. And so far, maybe you look at this and you're actually thinking, this doesn't look so bad. Photons and protons actually are quite useful because there's a lot of phase space on this plot that's still available to use to understand photons and protons. And in fact, this is what we've been doing up until this point, is using photons and protons to understand this white area of the plot. But I want to point out that this is a log scale on the y-axis. And so if you ask another question, which is where is the universe on this plot, you end up with the vast majority at the top. And this means that if we want to understand the universe, we're really limited if we're not able to use photons and protons at these higher energies. So the next follow-up question, if you know that this is a talk about neutrinos, is where are neutrinos on this plot? And the answer is anywhere on this plot, because neutrinos do not interact with photons in the same way that protons do. And so they're potentially capable of traveling the entire length of the universe before they interact. And that gives us a much better handle on detecting the neutrinos from these sources, even from very distant sources that are far away from us. So let us move now to the overview of neutrino astrophysics, and I will pause to take a drink. So what have we done so far in neutrino astrophysics? So I'd like to talk first about low energy neutrinos. So we have seen neutrinos from supernova in 1987A. This is a false image plot of the different optical emission that we've seen from the supernova, but we also saw neutrinos. And this actually we were able to use this to better understand the physics of the supernova themselves, which is really exciting. And of course, we've also seen neutrinos from the sun. You may have heard of the solar neutrino problem and how the neutrinos from the sun were able to help us understand additional features of the neutrinos themselves in terms of their flavors and how they switch between the different flavors as they propagate. That was something that we were able to use those solar neutrinos to learn. Then I want to talk about the higher energy spectrum, where we want to think about what are the possible sources in the universe that we know of that we think are big enough and energetic enough to accelerate neutrinos to extremely high energies. So here I've put 4 possible examples. We have neutron star mergers, we have active galactic nuclei, we have gamma ray bursts, and we have tidal disruption events. So those are 4 types of sources that may be neutrino producers, although we still need to figure out if these are really neutrino producers. These are, at the moment, mostly just hypotheticals that may be high enough energy to produce neutrinos. I also want to mention that we also expect cosmogenic neutrinos. This is something I'll talk about a little bit more later. And this is a type of neutrino that we expect from those cosmic rays that interact with the cosmic microwave background. One of the byproducts of those interactions can be neutrinos as well. And so that's an additional handle we'll have on detecting these neutrinos, or expecting these neutrinos, really. I also briefly want to mention that there's also particle physics that we can do with neutrinos. So even though neutrinos themselves are, we're hoping to use them as messengers, they themselves can be used to better understand particle physics. And part of the reason of this is because the neutrinos that we're looking for with my experiments are going to be describing collisions that have higher center of mass energies than are possible with the LHC. And so this is an additional handle we'll have on understanding features like the flavor ratios, inelasticity, cross sections of neutrinos. Those are all things that we'll be able to measure with these experiments at the very highest energies. So how are we doing on detecting these neutrinos at high energies? First, I'd like to talk about IceCube, the IceCube Neutrino Observatory, which has really led the way in trying to detect this astrophysical neutrino flux. So I know some people in the room work on IceCube, but in case you are not one of those people, IceCube is a detector at the South Pole. It is buried over a kilometer in the ice and is made up of hundreds of digital optical modules, which are also called DOMs. And these DOMs are detecting the Cherenkov emission from the neutrinos after they interact in the ice and create a shower of blue light. This here is the Eiffel Tower for scale. And I really want to mention that this is an incredible feat of engineering. The fact that we were able to build this so deep in the ice at the South Pole with all of the logistics constraints that come across with that, I personally at least am extremely impressed that we were able to build this. So how have we done? Here I have the same plot as before of flux versus particle energy. And you can see that the neutrino flux that IceCube has measured is shown here on the left. So this is a compilation of a few of the neutrino flux measurements that IceCube has made over the years compared to this cosmic ray flux that I showed you before. So number one, these neutrinos that IceCube is measuring are astrophysical, which is very exciting. That means they're coming from some of these sources that I was telling you about. One mystery, though, is that we still don't know where the majority of the IceCube neutrinos are coming from. And that means that there is more work to be done. And we have seen some evidence of a neutrino source from IceCube, but it's not a class of sources. It is sort of like sporadic sources like NGC 1068, as well as TXS 0506. Those are two examples of sources that IceCube has seen. But we'd like to know more about what is causing these neutrinos. And that's an open question that we still need to answer. But one thing I do want to point out is that we have seen the galaxy in the light of neutrinos, which I know some people in the room know very well. This is that same plot that I showed you before of optical and gamma ray emission. And now we also have the tools with IceCube to measure what the observed neutrino flux is from the center of the galaxy as well. And you can compare that to the predicted and the analysis expectation of those neutrino fluxes as well. And so this is really kind of coming full circle where you could imagine using these neutrinos as an additional messenger to help us understand the physics of the Milky Way, the physics of other galaxies, and I think that this is so cool. All right, so I've now gotten rid of the cosmic ray flux completely because I want to focus on neutrinos from here on out for the most part. And what I want to talk about are what is going on at this higher energy range from neutrinos. Because we have IceCube down here, and there's a lot of space left on this plot, and I'd be curious to know more about what are the neutrinos up here? What are we expecting? What have we measured? What limits have we set? And so I'd like to talk about that for a little bit now. So let's illustrate specifically what I mean by neutrinos, especially astrophysical versus cosmogenic. So here I have a source, and I have the Earth. I even have a little balloon as a preview for what Pueo will be in the future. And if you have a source, there's two types of neutrinos that you could expect. Number one, you have astrophysical. These are neutrinos that are created within the source and travel straight from the source to the Earth. Those are the types of neutrinos that we expect IceCube is measuring right now. And those will point right back to their source exactly like that. We also expect a type of neutrino called cosmogenic neutrinos. And in this case, we'll have a proton that is emitted from the source and travels some distance before interacting with the cosmic microwave background, and then traveling from that location to us here on Earth. The general idea here is that those protons can only travel to within about 50 megaparsecs of the original source. And so those, even though those cosmogenic neutrinos will not point exactly back to their sources, because these are such long distances, by the time they get to us, they basically will be pointing back to us. But this is an example of why we're expecting two different types of neutrinos from various sources. So with this image in mind, we can ask the question about what are our theorist friends telling us about the expected neutrino flux. And I've put 3 different models here in gray. So 2 of them are cosmogenic models. So those are models that are predicting how many neutrinos we might expect from those cosmic ray interactions. And you can see that those peak over here on the top end of the energy spectrum, which makes sense because we're expecting cosmic rays at the highest energy of the spectrum to be creating them. So that's great. We also have astrophysical neutrinos, which are included at this lower edge. And so we are expecting potentially both types of neutrinos to be created in the universe. And this especially is motivating looking at the higher energies, because there's reason to believe that there may be neutrinos at those higher energies as well. So, of course, IceCube and actually Auger, our friend Auger, have both looked for neutrinos at these higher energies, and they have set limits. And with a limit, as a reminder, a lower limit here is better. So lower on the plot means a better limit, which means you've eliminated more potential models. And you can see that Auger and IceCube are tracking pretty close to each other with these current limits. And to set these limits, IceCube and Auger had to look for approximately 9 years and 15 years each. And we have a log plot here, so that means that each improvement comes with a cost, either a time cost, a size cost, and an analysis cost. And so when we're thinking about scaling up to bigger and bigger energies, we have a few options. Number 1 option is to improve this limit through better calibration, better analysis. But what I want to think about are specifically, what do you do on a larger scale? And so your choices are, in general, sort of 3 different choices. Number 1, you can wait decades to build up more analysis live time in your experiment. Number 2, you could build many ice cubes, expand the area that you're observing. And that's also an option that's on the table. But what I want to talk about today is trying something else. What other techniques do we have to sort of target this highest energy range? And so what I'd like to propose is, instead of using optical, we can use radio, because at the very highest energies, what happens is when a particle like a neutrino comes in and slams into the Earth in the ice, what happens is a particle cascade that overall develops a negative charge excess. And that charge excess has a width, a physical width in space, which is about 10 centimeters. And that physical width will be traveling at a speed faster than the speed of light and ice, and that shower is going to have an overall negative charge excess. And because of that, it is going to radiate, and that radiation will be coherent for wavelengths that are greater than the width of that shower. So I've illustrated that here, where you have small emission coming off the shower, and those will not necessarily add coherently, where these larger ones, no matter where the emission is happening within the shower, that emission will add coherently. And so it turns out that ice is actually a very natural, ideal medium for this type of interaction. That's because it is radio clear, it is dense, it is dielectric, so this type of an effect will happen. But we also have an additional advantage, which is the attenuation length. So how long does a signal travel in ice? And if you think about IceCube, the attenuation length for optical wavelengths in ice is about 80 meters or so, whereas for radio, it's closer to a kilometer. And what this means in practice is that we can build a much smaller instrument to observe a much larger piece of ice. And that is a lot more efficient from an instrumentation perspective. So that's the technique that we're going to be using in the experiment that I'll talk about today. So as an example, we have the neutrino coming in, creating this particle shower and emitting radio. And if you were to, for example, put your radio antennas in the ice itself, you would imagine seeing a signal that looks something like this in your detector. So number 1, you're going to be expecting an impulsive radio signal. So that just means very short in time, or also very broadband in frequency. Number 2, you're expecting megahertz to gigahertz in terms of the frequency range, and that's because that's due to the Ascarian effect that I talked about just a few slides ago. And then finally, it's going to be likely originating from deep ice. And that just means that when we're trying to reconstruct that signal direction, it's expected to point back to where the ice is because that's where we think that the interaction is happening. So one option you have if you're building an experiment is to build something similar to IceCube in the ice, and that is what these experiments called ARA and RNOG will do. I don't have too much time to talk about them today, but I do collaborate on them. So if you have questions, I'm happy to take them. What we're going to talk about today is the balloon strategy. And the balloon strategy is, rather than look at a fairly small area of space for a long time, with a balloon, you can observe nearly the entire Antarctic continent, but only for a short time. And so that's the technique that we're going to be using in Pueo. I also just want to point out that this is really sort of a worldwide effort. So a lot of the experiments that I work on are sort of around the world at this point. A lot of them are in places with ice, but there are other techniques that we're looking into as well. Brian mentioned that I work on an experiment in California, which is called Beacon. This is taking advantage of a mountaintop type design. And so there's a lot of different ways of sort of trying to build an instrument that can see a radio signal. So I only have time today to talk about Pueo, but there's a lot of work being done both on other experiments that I collaborate on, as well as other experiments in the field. And so there's a lot of exciting work happening across the field. Okay, so coming back to this picture of flux versus energy, I've now added the radio experiments that have published limits. So all of these are published limits from the various different collaborations. And immediately it's clear that these are not yet competitive with OJ and IceCube, with the exception of ANITA, which is a balloon experiment, which is the world leading limit, sort of above 10 to the 20 at the moment. So this is, maybe looks like bad news for the radio. I've been hyping up radio, and now we're pretty far away from some of these other fluxes. But what I want to point out here today especially is that the radio experiments are in a lot of ways sort of prototypes, where we've been doing a lot of work trying to build and understand and perfect our triggering, our detection, our analysis. And at this point, we're really ready to scale up to be much more competitive with these other experiments. We've had to develop a lot of new technology, and we're sort of at a point now where we're ready to move into the big leagues. So that is what we will talk about today, about how we go from up here down to here. And so now we'll talk about Pueo, and I will take another drink. All right, so I am here on behalf of the Pueo collaboration. So please, if you take away one thing about Pueo, take away that we are a large team that are, all working really hard to get this balloon off the ground and taking data in about a year and a half. So, it's all of these different institutions that collaborate. This is us very luckily going to Hawaii for our collaboration meeting because we collaborate with the University of Hawaii. But truly, this is a team effort that is not possible without, many, many people doing many, many parts of the experiment. So I'm very grateful to this whole team for all of the work that we're doing to build this instrument. So Pueo is a balloon-based experiment that is looking for this Ascarian emission in the radio spectrum. We are hoping to fly for about 30 days in December of 2025, so just over a year from now. And this is actually going to include two different instruments, which I'll talk about today. So number one, we have the main instrument, which is up here, and number two, we have the low frequency instrument, which is below. So zooming in on the instrument in particular, this main instrument may look familiar if you're familiar at all with the ANITA experiment. So this is about the size of a minivan if it were on its trunk. It is launched from a truck in McMurdo. It is consisting of 96 what we call quad-ridged horn antennas, and that means that they are sort of cubic almost in person. They are dual polarized. That's a way of saying that we're expecting vertically and horizontally polarized signals to come in to our antennas, and we'll be able to detect both. We also have full azimuthal coverage, so these antennas go in all directions, all around the main payload, and they're targeting this 300 to 1200 megahertz band, which is ideal for the Ascarian channel. Number two, we also have this low frequency instrument, which will drop down off of this payload after the launch. These are 8 total, what we call sinuous antennas, because of their design here sort of going in to out. These are also dual polarized, so they're also able to see both vertical and horizontally polarized signals. And we are targeting a lower band of frequency with this instrument, and I'll describe why in a bit. So number one, they're between sort of 50 to 500 megahertz in general. And number two, they're made of fabric, so that allows them to be sort of folded up underneath the payload before the launch, and then released after we hit our main altitude. So why are we going to Antarctica to launch this? Number one, ice is really important for us, which is because of that Ascarian effect that I talked about before. But it also turns out that the NASA Long Duration Balloon facility has a launch point off of McMurdo, and that just is happenstance that it's over ice. That isn't, by design, it's just lucky for us because we really need that ice to be able to see our experiment signal. And our hope is that we're able to get at least 30 days of flying out of the Antarctic winds. And that's because these Antarctic winds will push our payload in a circle until eventually it will start veering off course, and then we'll have to cut it down. But this allows us to do this for a long time without going into the airspace of other countries, which is ideal for a long period of time. So you may have seen the ANITA balloon payload before, but if not, I have an example of one of those payloads here. And you might notice some immediate differences between these two instruments. Number one, they don't look like they're the same size, but they actually are the same size. And the reason they don't look like they're the same size is because we've shrunk the antennas. So the antennas used to be bigger, now they're a little bit smaller. That's because it used to be that ANITA turned on around 200 megahertz, and now we're turning on at 300 megahertz. The reason for this is because a lot of new satellites have come online that target that 200 to 300 megahertz band. And so we had to cut out a lot of that band in our analysis for the later ANITA flights, and it turned out to just be more useful to get more antennas, start our band a little bit higher, and get more antennas onto our payload. And the nice thing about this is that it allows us to have better reconstruction of our eventual physics signals. Number two, we have this new low frequency instrument. The reason that we're adding this is so that we can target what we call air showers, which are mostly expected to be cosmic ray signals, and I'll talk more about that in a bit. And then finally, I want to talk about something called the phased array trigger, and how that allows us to get to higher trigger efficiency. So generally in an analysis, one of the first things that you'll do if you see a signal that's interesting is you will point that signal back to where it came from. That's a very natural instinct to do. And what we've done with the phased array trigger is essentially move that step to the trigger level rather than leave it only in the analysis level. And so I have an illustration here that sort of shows how we do that in one dimension. So if you have 3 antennas that are listed here in a row, and you had a plane wave come in and hit these signals, you would expect that signal to hit, the first antenna, and then the second one, and then the third one. And you could predict with what delay you would expect. If you know the signal is a light signal, you can expect, if you know the direction, you know what the time delays are going to be. And vice versa, if you measure the time delays, you'll know what the direction was. And so what we can do is actually do this in our trigger, where we try multiple directions that have predetermined time delays, and those different directions we call beams. And if we take those signals and add them as if they're coming from all of these different directions. When we are right, those signals will add coherently, and when we are not right, those signals will add sort of incoherently, which I'll show on the next slide. And from this, we're able to improve our trigger efficiency and trigger on much lower SNR signals. So here is an example of the phased array in action in simulation. So here on the right, you can see what a typical signal might look like in our detector, where we have voltage on the y-axis versus time. So this is just a time trace of what our detectors are each measuring, what each of those antennas are measuring. And you can see here, buried a little bit in the noise, is what the signal would look like for each of those individual antennas. And by eye, you can definitely see it, but it's not a huge signal, right? But if instead you tried to do this technique of phased array triggering, where you try all these directions and add the signal up, what you get is a plot on the left. And in this example, this red beam associated with a specific direction is really, really strong at this location. And that allows us to really easily see in the trigger which beam is right and also which signal is real. And this is very powerful and improves our triggering capability by quite a bit. We also have now tested the phased array trigger in the field. This is me working at the South Pole as part of my PhD thesis. We were able to build a prototype phased array as part of the ARA instrument. This is me going there in, I think, 2018. In this picture, we had an internet connectivity problem where our instrument went offline. It was an extremely challenging problem to fix in the field because you would plug in a cable, go back to the base, see if it worked, and repeat for about 2 weeks until we figured out which cable was wrong. But we were able to test this in the field, and we know now that the phased array triggering model works. So let's talk about how we're designing it for Pueo in particular. So number one, we are using a new type of digitizer called the RF sock. This is something that is going to allow us to phase together many, many channels fast enough for us to trigger at a rate of about 50 to 100 hertz with Pueo. Here I have a picture of trigger efficiency versus SNR. So this is essentially, how efficient are we on a signal versus how strong is the signal. And here in green is that performance of that box that I just showed you a picture of at the South Pole. We also have the old Anita trigger efficiency. And then here we also have the predicted Pueo trigger efficiency that we're expecting from our new Pueo instrument. So we're able to do this with these RF socks in our hand. We are using various digital time processing strategies to do this, and we're expecting our trigger thresholds to sort of automatically adjust to meet our expected trigger rates. I'm going to take another break for my water. All right. So this is what Pueo looks like floating above the ice. And I want to talk a little bit about the expected physics signals that we're going to get for Pueo. So number one is our friend the Ascarian emission, which is expected to be pointing sort of back to the ice like this. It's going to be vertically polarized because of where we're looking at this Cherenkov cone. And it's not going to be reflected, which is maybe a strange thing to say, but it will make sense in a second. We actually also potentially expect another type of neutrino signal called a tau neutrino air shower. And this happens when a tau neutrino in particular interacts in the ice, creates a tau lepton, and then showers and hits our balloon. And in this case, we're expecting a less broadband signal, so lower frequency, horizontally polarized because of the direction of the magnetic field at the South Pole, below the horizon again because it's pointing back towards the ice, and again, not reflected. And then finally, we also expect direct and reflected cosmic rays. And this happens because cosmic rays themselves, those high energy cosmic rays that I told you about earlier, those will also interact in the atmosphere. and create radio emission. And those could be either direct or reflected, but if they're reflected, that means they're bouncing off of the ice and reflecting their polarity before they reach our instrument. So in that case, even though they'll be pointing down, they will be reflected, so we'll be able to tell the difference between those and any potential tau neutrino showers. So if you were to include this in a Venn diagram, this is what it would look like, where our Ascarian neutrinos are going to have features from all three of these categories of characterizations of signal, whereas these other types of backgrounds, or at least these two types of backgrounds, will really only have one or two of those features. And what this also means, though, is that we have to be really sure that we're building an instrument that can detect the polarity, the frequency, and the direction of our signals really, really well, so that we know for sure which category of event we're looking at when we are doing our analysis. I also want to talk about the ANITA anomalous events, which you may have heard of. So here I have 4 examples from the ANITA 3 instrument, and all of these are air showers that we saw. So these are potentially cosmic ray events that we saw with our instrument, and I want to focus on a few features. Number 1, whether they go up as their main feature or down as their main feature. And number 2, what is their angle? So the angle is here in the title. So this is -3 degrees. That's just below the vertical, which is just above the horizon, which is at about 6 degrees, -6 degrees. And then we also have this guy, which is at -36 and -35. So those 2 events are coming in very steep in our detector. And so if you were to categorize them, number 1, these would be reflected. This one would be a reflected event. And that's because we know it's coming from very far into the ground. And so we're expecting that to be one of those ones that bounces off the ice. Number 2, we expect these guys on the diagonals to be direct showers. That's because of their angle, and they're flipped in their direction relative to this guy. And so that's what I mean by reflected polarity. I mean it's the opposite signal sign that we were seeing before. So this is great. However, this final one is a bit of a mystery because it matches the direction of these light blue signals, but the direction is really, really steep. And that means that it's kind of half like a reflected shower and half like a direct shower. And in fact, this would be very similar to what I would describe a tau neutrino air shower to look like. However, we know it's not a tau neutrino air shower because it's not consistent with what we know about how neutrinos would interact as a function of angle. If we're seeing an event all the way down here at -35, we would have expected more events at more shallow angles as well. So this is what we call an anomalous event for ANITA. And in fact, ANITA saw this type of event in 3 out of the 4 flights. And this is not a signal that any other experiment has really been able to confirm. And that means that it's, number 1, very interesting, but number 2, worth following up on. And so a big question is whether Pueo will see more. And part of the motivation for the LF instrument is to help us understand this potential class of events better. So this low frequency instrument I'm showing here again, this is the layout that we're using for our 8 antennas. And here's another trigger versus single antenna SNR plot. Here we have the Pueo instrument again and 3 possible trigger curves for the LF instrument. This is an experiment that's really a work in progress, so we're still determining exactly what our trigger curve is going to look like for this instrument. But these are 3 possible options. We're kind of thinking this middle one is the most realistic at the moment. These are both a picture of our conductive fabric antenna as well as a diagram. These antennas are actually huge. They're 1.6 meters by 1.6 meters. So they are not tiny. Right now, this is a hand-cut prototype, but we're working with companies to sort of get real antennas out the door and ready for testing in the spring. And so one of the things you have to worry about a lot in this is that we want to deploy it well the first time. And so here's an example of us testing our deployment mechanism for the LF instrument in Chicago this year, and maybe it will play. Yes, so we essentially get one shot to do that right in the real instrument. We're testing it now in not ideal conditions, right? We're not in space or on the edge of space during this test, but we've been testing it in the lab, and then we will also test it one more time in a hang test next spring in Texas before we ship off to after we ship off to Antarctica. So very briefly, I would like to talk about how we can characterize cosmic rays. So this is the number of cosmic rays versus energy, and this is how many we will see with PUEO. PUEO, because it's a more sensitive instrument, is actually expected to see approximately 1,000 cosmic ray events. This is way more than what we saw for ANITA, which was on the order of 64 total cosmic ray events. And so this is going to allow us to understand this class of events much better, which is very exciting. You can also think about how many events will the low frequency instrument see in addition to the main instrument. So this is the intersection of events between the main and the LF instrument. So black here is what the main PUEO instrument will see, and then here are 3 possible intersection events that we would see in both the main instrument and the low frequency instrument. And what's really exciting about this to me is that even if it's not 100% of events that are seen by both instruments, even seeing 400 events in both instruments would really help us understand better like the frequency content, the direction, and really help understand if there are any potential anomalous events. We'll be much better positioned to characterize them and understand them. And then finally, I wanted to say that for the tau neutrinos in particular, there is a potential to see tau neutrinos and Ascarian neutrinos, and for those neutrinos to be coming from potentially even the same source. So this is a very dense plot, which I will briefly describe. So fluence is on the y-axis versus energy. So here in blue and red are 2 example fluxes you might expect from a source that is flaring for a short amount of time. And here in black is what we would expect PUEO's LF to see on the tau channel, the main instrument to see on the tau channel, and then the main instrument to see on the Ascarian. And so the idea here is that potentially the Ascarian and the tau channels could work together to both be seen from the same source, which would be really interesting and exciting. So if you wonder what our sensitivity looks like for PUEO, this is the flux versus energy of our detector. This is the same plot that I showed you before, except I've played a few tricks with the perspective to look at the highest energies with PUEO. And this is what the simulations team at OSU has been especially working on. So this is not our expected limit. This is our expected sensitivity for a single event. So you can expect a little bit worse of a limit if we didn't see anything, but this is just to give a ballpark of how sensitive PUEO might be. And the simulations team has worked hard to create this potential curve, as well as starting to answer some really fundamental questions about the detector. So, are there opportunities for us to use our simulation to better calibrate our instrument or calibrate it quicker once we've flown? Number 2, what does our simulation tell us about any firmware choices for our trigger? Are there ways of using our simulation to better understand the trigger that we're installing? And then number 3, how can we best use those 2 instruments together to best describe the physics signals that we're expecting? So I will mostly wrap up here. I just want to briefly say that there's other experiments that are also working on detecting this flux. We have ARA and RNOG, which are 2 of the ground-based detectors that I also work on. And then we finally have IceCube Gen 2, which is hopefully in the works. This is the IceCube instrument as it is right now, and we are hoping for bigger optical and an extension even into the radio for the future, which I think would be really exciting as well. So I will leave it here because I believe I am out of time. Generally, I think the next few years are going to be really exciting for PUEO especially. but also for the whole field, and even not seeing anything will help us understand better what our universe is creating. So thank you very much, and I will take questions.
Okay, questions? We'll start there. So, would two balloons have been better than one? I would imagine you would have more directionality or.
So that's a great question. So the question was, would two balloons be better? And the answer is 100% yes. And one of my crazy ideas would be to try to fly two balloons one after the other. Logistically, that's very hard to do because you would have to launch them at the right time. And so the biggest problem is logistics. From a physics perspective, if you could have two balloons that are marching right along each other, that would actually be really nice for various reasons. But it's not currently within the scope of what's possible given the balloon facility at McMurdo.
Okay, so marching along with each other would be required as opposed to just being aware of how far apart they are?
Sorry, I just mean like in the sky at the same time. They don't have to be like right next to each other, but observing approximately the same area at the same time, which they don't need to be super close for. Yeah.
So then what's the difficulty?
Because we would have to launch them, the actual activity of launching them is not always guaranteed. So you would not be guaranteed to launch them, you know, one after the other. There's really only one launching facility at McMurdo, and you have to wait for good weather conditions, you have to do some testing. So logistically, it's difficult to do one after the other like that, just from a practical perspective. And if there are days between each other, they'll be observing different ice, and then you lose the advantage of sort of seeing the same backgrounds from the two balloons. But of course, you know, if NASA wants to fund us to do two balloons, I think none of us would be mad.
Just launch one and have it on a tether and then wait for the rest.
Yeah, so the tethered balloon question is also very interesting and is something else that we're looking into. Again, to do a tethered balloon, you have to have special tethered balloon facilities, which do not currently exist over large swaths of ice, but it would be certainly interesting. And I would be very happy to explore that as a possible option. But yeah, logistically right now, it's easiest to do one balloon at a time, and then sort of look at the data, see how it looks, and then do another one a couple years later.
Actually, I have another unrelated question. You didn't mention total internal reflection of the radio waves in the ice. Is that because it's just not relevant, and why not?
Right, so the question is total internal reflection within the ice. So we do have to think about the Fresnel coefficients of the ice as we are going through the mediums. When we're going from an index of refraction of the ice to the air, you do get a reflection, you just get a Snell's law rather than a total internal reflection. You'll get a total internal reflection going from air to the ice, which you do have to worry about for the in-ice experiments.
I thought it was the opposite. The speed is faster in air than in ice.
Right.
So
it's about the, yeah, so the way that I think about it is with the direction, I'm pretty sure it's the way where you'll see it if it's in the air. If a signal is coming from the air, you will see total internal reflection at a specific angle.
can I ask a different question?
Sure.
And I'll stop. You showed, I got confused when you were showing the anomalous Anita events.
Yeah.
You pointed out that some signals went the opposite direction. It sounded like you were saying it was a deficit of intensity, but I can't understand. What's the significance of going down versus up on this graph?
Right, so here you can see how this one goes down and then up in blue.
Yeah, what does it mean?
So this is essentially what direction is the electric field pointing, like how the electric field enters our antennas. So the best way to think about this is relative polarity rather than absolute polarity, because the absolute polarity will depend on a lot of instrument-specific features. But since this was all detected with the same instrument, you can compare this event to this event to this event and see whether they are the same polarity or opposite polarity from each other. So in this case, you have 3 that we have that are sort of going up and then down, and then we have 1 that goes down and then up.
I see. So it's literally the amplitude of the field along a certain direction, and it's not an oscillating signal. It's got like a profile related to the source.
Yes. Right. So in this case, we have 1 example of an event that has a specific profile, and then 3 that have what look like the same type of profile. But if you look at the direction, you would actually expect these 2 to match each other in terms of their profile. And they don't. And so that's the problem. And we've seen this type of inconsistency on 3 of our 4 flights.
So I had just a general question. So when the balloon like starts leaving Antarctica, because of the winds or whatever, and you drop the payload, is there any plans to recover it or reuse it in any way? Because I feel like that would probably be the best option, but I haven't seen that.
Yes, so that's a great question. So yes, the answer is we do recover the payload, or at least we try, and that's part of what motivates us to cut it down while it's still over the ice. We hope to recover the hard drives that we're taking data on because we actually only send back a fraction of our data. Ideally, we would send back more, but we're limited to using satellite connections to send our data back. We are investigating whether something like Starlink could work to better send our data, but at least the Starlink terminal that we've tested so far is quite radio noisy. So if we use that, we would have to use it in sort of little bursts of time where we turn it on only for data transmission, because otherwise we'll swamp our own instrument. So it's a little bit of a work in progress to see if there are ways of transmitting more data. But right now we're expecting only a fraction of our data to be sent live, whereas most of our data will be on the hard drives on the instrument, in which case we are very motivated to go get it back.
Okay. Do you like have a parachute attached to it, or is it just kind of it falls and then just collect the rubble?
Yeah, I'm pretty sure there's a parachute, but it does crash. Like the instrument is not really reusable by the time it lands. Maybe some of the antennas are less affected than others, but the antennas act a little bit like a crash pad, and so they do crumple a little bit. And so, we'll assess the instrument once we get it back to see if any of it is reusable, but it's unclear. Usually we don't plan on reusing large swaths of it.
Maybe we'll take one more question.
Yeah, thanks for the nice talk. My question is, I can understand why you put that balloon to the specific location without using the ice, right? But there is still some sources from the, let's say, the lower angle. That's the astrophysical sources you mentioned. I'm wondering, can you use the current radio telescopes on the Earth? There are many telescopes, right? Can you detect such signals?
Right, so the question, if I'm understanding it right, is can we use existing radio telescopes to detect this type of signal? Is that right? Right, so a lot of times those radio telescopes are optimized for a different type of signal and a different type of trigger. So for us, we're looking for a very specific type of impulsive, short time window, pointing back at a location. It's a very different type of detector than a radio instrument that's observing, the whole sky or looking at a specific spot on the sky. There are other techniques you can use though. If you have a radio detector that's, in a field or on a mountain, you would be expecting to see a neutrino signal from that, or you could see a neutrino signal from that type of instrument. It's just that usually there's not a lot of overlap between the design features that we are looking for and the design features that radio telescopes are optimized for. But yes, you can build these experiments sort of anywhere in the world. It's just that they are a lot more sensitive if you are able to do them near ice or with specific geometric advantages. So yeah, ice is extremely helpful, and radio telescopes are generally not optimized in a way that will work for us, but you could technically see the signal anywhere.
Okay, let's thank Kaylee again.